optimization, artificial bee colony algorithm, gray wolf optimization, dragonfly algorithm, sine cosine algorithm, TLBO algorithm, etc. etc. So many algorithms are available. And here, one thing please remember that advanced optimization algorithms, they claim many advantages by saying that they can give the global optimum solution and complex optimization problems they can solve like that. Advantages are claimed by advanced optimization methods. Those are true. Those claims are true. But at the same time, please remember, even traditional optimization methods also give good results in some cases. For that matter, even traditional methods give exact values of the variables in less number of iterations or less number of generations as compared to advanced optimization methods. That is why I tell all these young researchers where what are the problems which they take up and they apply some genetic algorithm or PSO or ABC or any optimization algorithm. I simply ask them, Are, have you attempted any traditional method also to solve this problem? Just try it. And sometimes what happens, it happened in my case. 4 years back or so, we had applied our JA algorithm to some metal cutting problems, and we had produced the results and compared those results with genetic algorithm, PSO, ABC, etc., etc. And then one of the reviewers had asked us, what about application of a traditional method, like sequential quadratic programming? That is one traditional method, sequential quadratic programming. He asked us, you attempt that also and then include those results and make comparisons. Then when I had applied that sequential quadratic programming, which is a traditional method, surprisingly, I have seen those results are really good and almost equal to the J algorithm's results. Because J algorithm's results I already proved better than genetic algorithm, PSO or ABC like that in that paper. And then when I compared my JS results with a traditional method, sequential quadratic programming, those results are almost the same as J algorithm result. So that way I say that traditional optimization algorithms also perform better, in some cases. So don't look down upon them. Don't look down upon them. And at the same time, I say don't look upon it the advanced optimization algorithms. Whether they have their own demerits. And in general, I say whether traditional methods or advanced optimization methods, we are not biased. We should not be biased. Sometimes some problems can be easily solved by simplex method as compared to the so-called advanced optimization methods. That also we have experienced. And so for this problem, let us say for this whatever single objective optimization problems we discussed, or the two objectives, multi-objective problem we have discussed. Let us say I have applied all these methods. Suppose I know all these methods, traditional methods and advanced optimization methods. I have applied all these methods, and then suppose I found ultimately, suppose genetic algorithm has given. Okay, I ask Aparna this question. Aparna, you can tell me. Suppose I apply all these methods, and I have listed all the values of cost and efficiency. For cost and efficiency. Then which method I can say that is better? So many methods are there. There are so many methods. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, so many methods. Now, suppose I apply all these methods to this problem, to this bi-objective or two-objective optimization problem, cost and efficiency. Traditional methods I applied as well as advanced optimization methods I applied impartially, without any bias. Then Aparna, if I say I like that method which will give me the minimum cost and maximum efficiency, then am I wrong?
No, sir, this is correct.
Because मैं 10 methods apply करता हूँ, and वो 10 methods में से एक method has given me the minimum cost and maximum efficiency compared to other methods, then I say that method is the best one. Agreed or not?
Yes, sir.
Okay, now turn off your mic. Now, in that case, let us say genetic algorithm has given me the minimum cost and maximum efficiency. Then I can say, but I can say that the genetic algorithm has given me the optimum solution, optimum cost, and optimum efficiency. So, optimum solution I have obtained using genetic algorithm. You may say that. And you should not say genetic algorithm is the best. You should not say. You may say, you may say that genetic algorithm is the best for this problem. For this problem. That point you have to understand. For this problem, genetic algorithm may be the best. And but you cannot say that it is the best for all other optimization problems. We cannot say. We cannot say unless we apply it. Hmm? So there is a general feeling that no method is perfect, whether it is a traditional method or advanced optimization method. No method is perfect. One method which is suiting to certain type of problems that may not work well for some other type of problems. This problem, this is there, this issue is there. But that is why I always say, don't get carried away by one particular optimization algorithm. You have to learn as many as possible. Try to apply those methods to your research problems. Make comparisons and then bring out the positive features or negative features of those algorithms when you have applied to your research problem, and make analysis and write a research paper and get it published. Get it published. But don't get biased by any algorithm. Don't say that particular algorithm, genetic algorithm is the best, or PSO is the best, or Gray Wolf optimizer is the best, or TLBO is the best. Don't say that, because those may be the best for certain type of problems. For certain type of problems, they may not be the best. They may give good solution, but they may not be the best. In particular, one problem, say Gray Wolf optimization method has given best result, and in another problem, TLBO may give best result. In another problem, genetic algorithm may give best result. So that way, you have to learn as many methods as possible, and then make applications and make comparisons. So with this now, okay, population-based optimization algorithms. What is this population-based? Population-based means with how many number of initial solutions you are starting. Guess solutions. Guess solution or random solutions, we say. Random solutions. Instead of starting with one solution, we assume a set of solutions are there. 10 solutions are there. Then we say population size is 10. And if we assume 20 solutions in the beginning, random solutions, then population size is 20. So that is based on this population concept. Many algorithms have been proposed, like this as evolutionary algorithms, swarm intelligence algorithms, some other algorithms based on different phenomena. So many algorithms. The algorithms which I have written, these are very few. Which I have written, these have gained reputation. They have their own reputation, and they have been accepted by the researchers, optimization researchers across the globe. They have applied to their respective fields and they have reported good results. And but I have not listed many other algorithms. Those are also having a good reputation. What I mean to say, there are dozens, many optimization algorithms are available in the optimization field. These are all advanced optimization methods. And then population algorithms based algorithms have been applied successfully to various engineering optimization problems. All the population based algorithms require common controlling parameters like population size and number of iterations. That means with how many initial solutions you start with, that is called population size. Number of iterations means after how many number of iterations you will stop running the program. These two are required for any optimization algorithm. It may be genetic algorithm or PSO algorithm or ABC algorithm or TLBO algorithm. These are required. So these are called common parameters. Common parameters means any population-based algorithm requires this population size and number of iterations. And what is the meaning? If you change the population size, the result may be different. Suppose you are running genetic algorithm with a population size of 10, then the objective value will be something. But if you run the problem with population size of 20, then objective value may be some other thing. And if you run with the population size of 30, then objective function value may be some other thing. So that means population size is having effect on the final solution. Similarly, number of iterations is having the effect on the final solution. If you consider number of iterations 100, then you may get some final solution. If number of iterations 200, then the solution may change. That means population size changing is having effect on the final solution. Number of iterations changing, it is also having effect on the final solution. So these common parameters, finding out the optimum population size and optimum number of iterations itself is an optimization problem. And हम इसमें लटकते हैं. But in addition to that, there are some other parameters known as algorithm specific parameters, algorithm specific control parameters. For example, if you take a genetic algorithm, that uses selection operator, crossover probability, mutation probability, like that. So let us say crossover probability of 0.9, mutation probability of 0.05, and selection operator, that roulette wheel selection. Then when you run that program for a population size and number of iterations and the crossover probability of 0.9, mutation probability of 0.05, and selection operator roulette wheel, you may get some final solution. But that final solution may not be the optimal solution. If you change the population size, number of iterations, and the crossover probability value, mutation probability value, and selection operator, then some other solution you may get. And for some other probability, crossover probability and mutation probability, you may get some other solutions. That means by changing these selection operator, crossover probability, mutation probability in genetic algorithm, you may be having different solutions. Then the problem is, which solution is the real optimum? That is the question then. Then already हम लटक रहे हैं, population size कितना है और this number of iterations कितना है. What will be the optimum values? We are already struggling with those common parameters. But these specific parameters to genetic algorithm, like the selection operator, crossover probability, mutation probabilities, by changing those also, our final solution is changing. That means problem to our बढ़ गए. That means then what to this designer or decision maker? How he has to do? He has to design. He has to make a number of trials. That for a different crossover probability combinations of different crossover probabilities, mutation probabilities, selection operators, and then different population sizes, different number of iterations. So many trials he has to make. Ultimately, particular combination of population size, number of iterations, crossover probability, mutation probability, selection operator, that may give us the optimum solution. But that also we are not sure. After doing long exercise of trying different combinations of population size, this number of iterations, selection operator, crossover probability, mutation probability, after doing many trials also, one trial may give the best solution. But हम उसको भी भरोसा नहीं कर सकते हैं. What is the guarantee that is really the best? Still some much better or much better than that best value we may get it. Then we have to go on trying. Then how much we will try? This will increase the burden on the decision maker or the designer who is dealing with this optimization problem. So that way problems are there. Similarly, if you take PSO, particle swarm optimization, that uses inertia weight, social and cognitive parameters, W, C1 and C2. And those are having some again ranges. C1 can vary between 0 to 2, C2 can vary between 0 to 2, and similarly the inertia weight. Then by changing these specific parameters, different combinations of these inertia weight, social parameter, cognitive parameters, and that population size and number of iterations. ये सारे करके finally we have to find out which combination of population size, number of iterations, inertia weight, social parameter, cognitive parameter gives us the best value of the objective function. And a lot of effort is required. It itself is becoming one optimization problem. Finding out the optimum parameters of the algorithm is becoming itself an optimization problem. Why the decision maker or designer should be burdened with this? So if you see other optimization algorithms also like ABC, Harmony Search or ACO like that, they require these specific parameters. And that was why in the improper tuning of these algorithm specific parameters may either increase the computational effort or yield local optimum solution. That means selection of these control parameters, that is very important. That is very important. But how to achieve that? A number of trials we have to make. वो कैसे करेंगे? Lot of time is required, efforts are required. So keeping that in mind, in the year 2011, one algorithm was developed that was TLBO, Teaching Learning Based Optimization Algorithm. It was developed in 2011 with the idea that at least these specific parameters, algorithm specific parameters should be avoided. Population size and number of iterations, okay, we try to manage them, but these specific parameters like crossover probability, mutation probability, selection operator in genetic algorithm, inertia weight, cognitive parameter, social parameter in PSO, we can avoid them. If we can avoid them, that is better. So this algorithm was the first algorithm in the field of optimization, which was proposed as algorithm specific parameterless. That means parameterless algorithm. Parameterless means that a specific parameterless. Like genetic algorithm, it is not having any specific parameters. Like PSO, it is not having any specific parameters. These common parameters like population size and number of iterations, those are required here also. We have to try different combinations of population size and number of iterations. वो तो है. That problem is there with all population-based algorithms. The advantage of this TLBO algorithm is it is not having any algorithm-specific parameters. So that burden of tuning those parameters, that is not required here. It works on the philosophy of teaching and learning. TLBO algorithm has no algorithm-specific parameters for its working. Working of TLBO is divided into two parts. First part is called teacher phase and the second part is called learner phase. Here the basic philosophy is we have considered two stages. How the learning takes place. Like in the classroom, the teacher disseminates knowledge to the students. That means information is passed from the teacher to the students. Knowledge transfer is from teacher to the students. That is the teacher phase. Teacher tries to improve the mean result of the class. And now, what is the second stage, learner phase? In learner phase, we assume that there is interaction among the learners. Outside the classroom. That maybe in the hostel or like that, they interact. Like student A or student P interacts with student Q. P interacts with Q, and then about some subject matter, some doubt. Then if Q is knowing that, then he will inform that to P. Knowledge transfer is from Q to P. That way, interaction among the learners. And so these two phases we considered in the beginning. Later, some other phases were also considered, like tutorials and the independent study, that is self-study. All those concepts were introduced later. But the basic TLBO algorithm that consists of only two phases, teacher phase and learner phase. In the teacher phase, knowledge transfer is assumed to take place from the teacher to the students. And in the learner phase, after the class is over, the learners interacting among themselves and knowledge transfer taking place. These two phases. And then how, already as we have attended these optimization sessions, You have the idea about objective function, all that. Now, what is our objective function? Here, what we take the student to how many subjects we are teaching to the students, that we consider as the number of variables. That is, if two subjects are taught to the students in a semester, then design variables we consider as 2. If 5 subjects are taught to the student in a semester, design variables we consider as 5. So number of subjects taught, that is considered as analogy. Analogy, if we make number of subjects, that is equal to number of these variables, number of variables, and objective function value is nothing but the result of the student. So that is the analogy. And now let us consider, to understand this TLBO algorithm, I am not going to teach you any theory. I will try to explain the philosophy of this teaching learning based optimization algorithm, TLBO, by means of a tutorial. For that, we start with this flowchart. Aparna, you are able to see this flowchart?
Yes, sir.
Okay. The flowchart, yes, what is there on the top? Decide the number of students. Number of students we are considering as population size. Number of students in the classroom, we can say we make analogy with the population size. Then subjects. Subjects means decision variables. How many number of subjects? Those are equal to number of decision variables. Then termination criteria. Termination criteria can be any, which you can decide. It may be number of iterations. After how many number of iterations you want to stop running the algorithm, and or it can be time. You may specify some time. Say after 1 hour, this program should be stopped. That can be the termination criteria. Or it can be any desired accuracy. You may mention, if accuracy is this much, then program can be stopped. It is up to you. Termination criterion you can decide. Normally it is number of iterations. So now, for the sake of demonstration, I consider here 2 variables. That means 2 subjects are taught to the students, and classroom 5 students are there. Because I cannot tell you 60 students class example. Just for a demonstration, I have prepared a table. You can see this is a tutorial for solving unconstrained optimization problems. For that, I have taken up one objective function, that is called Himmel-Blah function. Objective function is to find out the values of x1, x2 that minimize the Himmel-Blah function. Himmel-Blah function minimize fxi equal to x1 square plus x2 minus 11 whole square plus x1 plus x2 square minus 7 whole square. This is the minimization function. Known. This is a standard benchmark function for which answer is already known. And the ranges of variables x1 and x2 can take any value between -5 to 5. x1 and x2 can take any value between -5 to 5. And then you try different combinations of x1 and x2, you will get different values of fx. Then for a particular combination of x1 and x2, you may get the minimum value. That will be considered as the optimum value. In this case, the known solution to this problem is x1 equal to 3, x2 equal to 2. x1 3, x2 2. If you substitute those values, then you will get a minimum value of fx at 0. For example, x1 you substitute 3 square plus 2 minus 11 means 0. Plus next term x1 3, x2 2. So 3 plus 2 square minus 7. That is also 0. So 0 square plus 0 square, that is 0. fx is 0. So minimum value of fx is 0 for x1 equal to 3 and x2 is equal to 2. That solution is known. But when you say that you have developed an algorithm, that algorithm you have to test on hundreds of benchmark functions, simple to complex, simple benchmark functions to complex benchmark problems. This is a simple benchmark function for demonstration I have taken. It is consisting of two variables, and okay, single objective, and ranges of variables are given -5 to 5. x1 and x2 can take any value between -5 to 5. And now you see how I have done. You can see this table 1, initial population. initial population. I have considered 5 number of students. Population size I have considered as 5. 1, 2, 3, 4, 5. And here 2 variables I have considered. In this problem, anyway, 2 variables are there. So x1 and x2. And you see learner 1, his x1 value 3.22 and x2 value 0.403. And the fx value how we have got, substituting this x1 of 3.22 and the x2 of 0.403 in the objective function. Objective function here is x1 square plus x2 minus 7 whole square plus x1 plus x2 square minus 7 whole square. I have substituted the values of x1 and x2 of learner 1, and I got fx value of 13.13922. And similarly, second learner x1 and x2 values. And please remember, these x1, x2 values for all these 5 learners are generated randomly. Because this, what are the ranges of these variables x1 and x2? -5 to 5. -5 to 5. Na? They can take any value between -5 to 5. So randomly I have taken some values. Some values within the given range. And here, incidentally, the randomly taken values are all positive. But as x1 and x2 can take any value between -5 to 5, some of the values can be negative also. But with a random, I have taken randomly, so these are the random values. In your, when you write the program, and in that program, once you write the ranges of the variables, then randomly chosen variable values will be written here for x1 and x2. And then substituting these values of x1 and x2 in the fx objective function, we have got the last column. And then what is our flow chart? If you go back and see the flow chart, first one is decide number of students, population size. Population size is 5 in our case. Subjects, decision variables, that is 2 in our case. Termination criteria, let us say 100 iterations. But I am not going to explain all 100 iterations. Only one iteration I will explain. Then what is the next block? Calculate the mean of each design variable. That means what? Now under x1 is having here 5 values. Find out the mean. Of that. Find out the mean means what? Now what we do? Now let me do this way so that you can understand better. Okay. Now, Aparna, you are able to see this?
Yes, sir.
Okay. Now, x1, x2, x3, x4, x5, I have taken the mean. Mean is 2.093. And similarly, for all considering all these 5 values of x2, I have taken the mean of x2, 1.697. So, mean of each design variable is calculated. And then what is there in the flowchart actually? What is there in the flowchart? If you see, the flowchart is saying this way. According to the flowchart, after, okay, just 1 minute. There is some disturbance. Now, in the flowchart, if you see, second block we have completed, calculate the mean of each design variable. Then third block is identify the best solution. So, in the classroom, who is the best means we normally say the teacher. That is why best solution is considered as the teacher. Of course, we know those who are in teaching profession, they must have experienced. Sometimes the students, they are more smarter, they are more intelligent than the teacher. But for the time being, we assume no one can be better than the teacher. So then here, best solution we have to identify. Now, ours is a minimization problem. So out of these fx values available here for all 5 learners, whichever is the minimum, that is considered as the best value. Aparna, what is the best value here? Best fx?
13.13922.
So 13.13922 is the best value. This is the minimization problem. That is why we have taken the minimum value. But if it is maximization problem, then which value we take, Aparna? If it is maximization problem?
261.57319.
So 261.57319, that we will have taken. Okay, we will have taken as the best value. So that way you can understand our logic, our TLBO method logic is applicable both for minimization problems as well as maximization problems. Whichever is the best that we take. In the case of minimization, the minimum value is the best. And in case of maximization, the maximum value is the best. So best value we take. And then after understanding this, we go to the flowchart. Flowchart, what is written after identifying the best solution? Yes, Aparna, what is written after identifying the best solution?
Modify solution based on best solution.
So modify the solution based on best solution. Some equation is given. So what we do for that, we are modifying. You see the bottom of the table. Difference mean x1. For x1, we are calculating for modification. Some random number is taken. Random number between 0 to 1. That random number, what we are taking, is between 0 to 1. Any value between 0 to 1. You need not bother when you write the program in MATLAB or Python. That provision is there to choose the random numbers. You need not choose, that program automatically chooses the random numbers. Okay, let us say for demonstration's sake, random number for x1 is 0.25, 0.25. Some random number multiplied by the best x1. Now what is the best fx value here? 13.13922. So corresponding value of x1, 3.22 is called best x1 and 0.403 is called best x2. So now to calculate difference mean x1, we are doing some random number r multiplied by best x1 minus mean of x1. Best x1 is 3.22 and mean of x1 is already calculated here, 2.093. 2.093, it is already there. So best minus, you please understand how difference mean x1 is calculated. Some random number multiplied by best x1 minus mean of x1. So that value is 0.28175. Then similarly you calculate for x2. Difference mean x2 is some other random number, any number between 0 to 1. Suppose it is 0.43. This random number 0.43 multiplied by best x2. So best x2 is 0.403 because best fx is 13.13922. Corresponding to that, best x2 is 0.403. So best x2 minus mean of x2. Mean of x2 is 1.697. So you substitute that. So difference mean x2 is calculated as some random number multiplied by best x2 minus mean x2. Best x2 minus mean x2. That is coming as minus 0.55642. So this is the way how we calculate it. This is table 1. Table 1. Why we are calculating all this? Because we will not stop here, because these are randomly generated solutions. Ultimately, we want to get the optimum solution. We want to go ahead. We want to move forward. So what we do, we go on modifying the x1 and x2 values like this till we get the optimum values. So now as the next step, what we do, we are actually modifying. How we will modify this difference mean x1, which you have calculated 0.28175, you add to this x1 column. Each element of x1 column is added by this the difference mean x1. 0.28175 is added to all these values under x1. Similarly, difference mean x2, that is minus 0.55642. This is added to all the values under x2 column. Added means as it is. For example, what is the new value of x2? That is this old value of x2, 0.403 plus minus 0.55642. Because ये तो difference mean x2 is in minus ना. So minus 0.55642. So what will be the new value of x2 here? That 0.403 plus minus 0.5564. And what is the new value of x2 for learner 2? That is this old value 2.289 plus minus 0.5564. That way the calculation goes on. So in simple words, you can understand the difference mean x1 is added to x1 column, difference mean x2 is added to the x2 column. By doing that, we have got table 2 with the modified values. So this is table 2. New values of the variables and the objective function. New values of the variables and the objective function. These are the new values of x1 and x2. Then with these new values, you make substitutions. That means for learner 1, the x1 of 3.50175, x2 value of minus 0.15342, you substitute in that fx equation, objective function. Then you will be getting 13.30313. And for learner 2, x1 is 0.47275, x2 is 1.73258. You substitute these values in the objective function, you will get 94.22118. Like that, for all these x1, x2 values of the learners, you substitute in the fx and you will get these. So these are the new values of the variables and the objective function. This is table 2. Now let us go back to the flowchart. If we go back to the flowchart, what step we have completed? Fourth block we have completed. Modify the solution based on best solution. That new value equal to that old value plus some random number multiplied by best x minus mean of x. Now what is next? Aparna, what is next in this flowchart?
Then we have to check whether the new solution it is better than existing one.
So is new solution better than existing? And that means table 2 is to be compared with table 1. fx values of the learners, those are to be compared with the previous table values. If new solution is better, we accept it. And then if new solution is not better, then we reject the new solution and we keep the previous solution. That is our understanding. So now if we go to our table, now table 2 with the new values is this. And for learner 1, what is the new value? 13.30. What was the old value? 13.13 in table 1, fx value for learner 1. So old value is better because it is minimization problem. Minimum value is better. So we ignore the new solution and we keep the old solution only in our table 3. Next is table 3. And now old solution for learner 2, that is 77.71. 77.71 is the fx value for learner 2 in the old solution. And in the new solution, that is 94.22118. So as it is minimization problem, whichever is lowest, that is better. So that this old solution is better. For learner 3, old solution is 14.02. And same learner 3, new solution is 12.76. Here this is minimum. So 12.76 we take here. And the new solution for fourth learner is 136. What about the old solution? 261. 261 for the fourth learner. That means new solution is better. And old solution for learner 5 is 43. And here 39. You can see the last element, 39.32602. That means this new solution is better. So this way, what we are doing, we are comparing the fx values of table 2 with table 1, whichever is better, that we take to table 3. So table 3 is this. This table 3 is called updated values of the variables and the objective function based on fitness comparison. And here we can make the analogy that the teacher has tried to improve the average mean result of the class. That is the analogy. And teacher phase is over now. After comparing table 2 with table 1, whichever are the better values we have kept in this table 3. Now what next? We go to the this flowchart. Yes, Aparna, what is written now in the flowchart?
Sir, after that selection, that is select two solutions randomly
Select it. Okay, turn off your mic. Select two solutions randomly. Select two solutions randomly. Now there are 5 students. 5 students. Now learner 1, learner 2, 3, 4, 5. That 1, 2, 3, 4, 5 not written here, but you understand learner 1, 2, 3, 4, 5. That column is also there. Now learner 1 is to be now interaction. Now this is learner phase is entering. The learners interact with each other. And in this TLBO algorithm, what we assumed, each learner will interact randomly with any one of the remaining learners. With any one of the remaining learners. Suppose that means learner 1 can interact with learner 2 or learner 3 or 4 or 5. Anyone. Any one of the remaining learners he can interact. So learner 1 interacting with, let us say he is interacting with learner 2. He is interacting with learner 2. And this can be random interaction. Learner 1 can interact with learner 4 also. That program will automatically take care of it. But here for our understanding, let us say first learner is interacting with the second learner. And whose objective function value is minimum, if you observe, 13.13 is less than 77.71, as ours is minimization function, this 13.13 is better. That means our first student is better than the second student. First student is better than the second student. Then the knowledge transfer should take place from first student to second student. Because first student objective function value fx is better than objective function fx value of the second student. So first student is better than the second student. Knowledge transfer should take place from the first student to second student. So then now table 4. Now table 4 we are going to prepare. That means again new values of x1 and x2 we want to calculate for all these 5 learners. Now first learner is interacting with the second learner. Now what will be the new values of x1 and x2 for the first learner? Now I will demonstrate. What will be the new values of x1 and x2 for the first learner? So here what we do then, how the new value is calculated. Please pay your attention carefully here. How I calculate the new value of x1 for the learner 1? I take this old value 3.22 plus some random number, any value between 0 to 1. So 3.22 plus random number multiplied by 3.22 minus 0.191. Why I am taking this way? Because first learner is knowledgeable than the second learner. Because first learner's fx is better than the second learner's fx. That is why knowledge transfer should take place from the first learner to the second learner. That is why when I calculate new value of x1 for learner 1, how I calculate this old value 3.22 plus random number multiplied by in brackets 3.22 minus 0.191 I keep. Whichever value comes, that I take it as a new value of x1 for learner 1. And similarly, new value of x2 for learner 1. New value of x2 for learner 1. How I calculate this old value 0.403 plus some random number, any random number between 0 to 1. 0.403 plus random number multiplied by in brackets 0.403 minus 2.289. So that will be the new value of x2 for learner 1. You can see now how I have done this way. Table 4. You see here x1 value, x2 value. These are the new values of x1 and x2 for learner 1. And after substituting those values in the fx equation, I have got as 112.32465. This way I have calculated. And now, okay, that is about the first learner. Now let us go back to table 3. First learner's new values of x1 and x2 are calculated. Now let us come to the second learner. This exercise we have to do for all learners. So second learner, he can interact with any one of the remaining learners. Anyone. Second learner can interact with 1 or 3 or 4 or 5. So let us say he is interacting with the fourth learner. Second learner interacting with fourth learner. And who is intelligent? Aparna? Aparna, who is intelligent, second or fourth learner?
Second one, sir. Second.
Second, because his objective function value is 77. Fourth learner objective function value is 136. So it is minimization problem. So whichever is minimum, that we consider as the best. So second learner is best as compared to fourth learner. So knowledge transfer takes place from second learner to fourth learner. Now, how to calculate new values of x1 and x2? How to calculate new values of x1 and x2 for learner 2? For learner 2, same approach. Like the old value of x1, 0.191 plus some random number multiplied by, in brackets, 0.191 minus 1.94175. Because this is x1 value of learner 4. That is why. Please listen again. A new value of x1 for learner 2 will be this 0.191 plus some random number multiplied by, in the brackets, 0.191 minus 1.94175. And what is the new value of x2 for learner 2? That is this 2.289 plus some random number multiplied by, in brackets, 2.289 minus 4.03658. That way we will calculate new values of x1 and x2. I have calculated and I have kept here. For the second learner, x1 is 1.27423, x2 is 1.63612, and substituting those values in the objective function, 2 versus 5. Okay, I have told you 2 interacted with 4, but okay, 2 interacted with 5. Then 2 interacted with 5, okay, let me tell you that concept only. 2 interacted with 5. Aparna, now you see, learner 2, if he is interacting with 5, who is better, second one or fifth one?
Fifth one, sir.
Huh?
Fifth one.
Second and fifth one, if I compare, then fifth one is better. Because fifth student objective function value is better than the second student objective. That means knowledge transfer should take place from fifth student to second student. So now if we now calculate new value of x1 for learner 2, that will be 0.191 plus some random number multiplied by, within brackets, we write 2.49575 minus 0.191. Aparna and other participants, please understand. Because why old value anyway we will take 0.191 plus some random number multiplied by, I am not taking it as 0.191 minus 2.49575. I am taking it as 2.49575 minus 0.191. The reason is fifth candidate is better than the second candidate. Knowledge transfer is from the fifth candidate to second candidate. That is why when I calculate new value of x1 for learner 2, I calculate it as 0.191 plus random number multiplied by, within brackets, 2.49575 minus 0.191. And now similarly, how I calculate new value of x2 for learner 2, that is this old value 2.289 plus some random number multiplied by, within brackets, I write 0.31058 minus 2.289. I will not write 2.289 minus 0.31058. I will write it as 0.31058 minus 2.289. Because knowledge transfer is from fifth student to second student. So that way I do. After I did that, second student interacting with fifth student, I have got the values of x1 and x2 as 1.27423, 1.63612, and fx value as 69.20665. And similarly, other interactions. Third student can interact with any one of the remaining student. He can interact with the first student or second student or fourth student or fifth student. So let us say third student is interacting with the first student. Now Aparna, tell me, who is better, third student or first student?
Third student. Third student.
Third student is better because his objective function is 12.76507. Then knowledge transfer should be from third student to first student. Then how we calculate new value of x1 for learner 3? That is this old value 3.46375 plus some random number. Then within brackets 3.46375 minus 3.22, because knowledge transfer is from third to 1. That is why the new value is calculated as this old value plus random number multiplied by this 3.46375 minus 3.22. Similarly, how I calculate new value of x2 for the third candidate? This old value minus 0.221 plus random number multiplied by minus 0.221 minus 0.403. This way I calculated, and this you can see in table 4 for learner 3, new value of x1 is 3.57831 and new value of x2 is minus 0.42692. Corresponding value of fx is 12.39108. This way. Similarly, fourth student interacting with any one of the remaining students. Here for demonstration, I assumed fourth student interacted with fifth student, and similarly, fifth student can interact with anyone. Here I assumed that fifth student interacted with fourth student. After that, I did all these calculations, and this table 4 is containing the new values of the variables and the objective function. New values of the variables and the objective function. And then next what? Next what to do? Now let us go to the flow chart. What to do? Now you see, Aparna, you see, we have selected two solutions randomly, P and Q. And here, this diamond is saying if who is better, P is better or Q is better. That means which student is knowledgeable. If P is better than Q, then you see new value of x equal to old value plus random number. Then knowledge transfer is from P to Q. That is why you can see here JPI minus JQI. Knowledge transfer is from P to Q. If P is knowledgeable, then Q. If not, then left side. If P is not knowledgeable, then Q, then you can see here in brackets, here new value equal to old value plus random number into Q minus P. Knowledge transfer is from Q to P. So this exercise we have done. Then what is the next step, Aparna?
Is new solution better than existing one?
That means now table 4 fx values we have to compare with the table 3 fx values. New solution is better than the previous. If new solution is better than the previous, we accept. If new solution is not better than the previous, then we reject the new solution. We keep the previous solution. So now that means table 4 is to be compared with table 3. हम यहाँ से जाएंगे table 3, just to see learner 1. Learner 1 fx is 13.13. Table 4 compare करना है. Table 3 and table 4. Okay. 13.13 for learner 1, and a new table 112.32. Now, Aparna, which is better? New solution is better or old solution is better?
Sir, new solution is better when we compare for the interaction between third and first learner.
Because now old solution is better because old solution is 13 point fx values you can see in the last column. For learner 1, 13.13. But in the new solution, if you see the fx column, for learner 1 it is 112. So,
but sir, for third and one learner value it is minimum.
Anyway, you turn off your mic. Your mic is not audible clearly. Just you please understand the procedure. So fx values comparison is done. Whichever fx is better, that fx value we take further. Here it is minimization problem. So whichever value is smaller, that we consider as better. Now I give you another just to demo example of this learner 2. Learner 2 new value of fx is 69.2. 69.2 is a new value of fx for learner 2. And if we see the old solution, that is 77.7 for learner 2. That means the old solution is not better. New solution is better. That we keep it in the next table 5. And for the third solution learner, the old solution is 12.7. Third learner, the new solution here is 12.39. So that way new solutions and old solutions are compared. Whichever is better, we have taken to table 5. We have taken to table 5, and this table 5, these are the updated values of the variables and the objective function based on fitness comparison. Then what to do? At the end of this first iteration, now we have got minimum value as 12.39. Best value is 12.39108, and corresponding to that best x1 is 3.57831, best x2 is minus 0.42692. And now let us see the flow chart. What to do next? Here you see, if new solution is better than the old solution, we accepted it. If not, we rejected the new solution, we kept the previous solution. And what next means is termination criteria satisfied. We have completed one iteration we have completed. And but in the program, we will not stop with one iteration. We may write 100 iterations or 200 iterations like that. So answer is no. When answer is known, then where it goes? It goes back here. Calculate the mean of each design variable. Again, this cycle, this repeats. Calculate the mean of each design variable, identify the best solution. Now that means what? Here in table 5, we have identified the best solution, 12.39108. Then these x1 values, all these x1 values, so take the mean of that, calculate the mean of that. Similarly, x2 value, calculate the mean of that. Then difference mean x1 can be found out. Difference mean x2 can be found out. Then difference mean x1 can be added to the x1 column. Difference mean x2 can be added to the x2 column. Then next table 6 contains new values of x1 and x2 and corresponding to new values of fx. Then making comparison. So this procedure goes on. And this way, of course, there is a tutorial for constraint optimization problem also, but as time is short, I cannot take up. But let me just to show you Science Direct. Let me show you the Science Direct for just a few minutes. And let me hope that internet is working now. Let us see. Science Direct. ScienceDirect.com. And I have actually made this TLBO algorithm code public. So this is available in Google search. If you just simply type TLBO algorithm code, then you will approach that website, and the code is written in MATLAB. Now let me type as teaching learning based optimization algorithm. Learning based optimization. These words I am typing in Science Direct. Just to search for the research papers. Those are available. Now you can see here. You can see hundreds of research papers in this Science Direct itself using this teaching learning based optimization algorithm, TLBO. And here you see the title, a hybrid, and just let me make it bigger so that you can read it. A hybrid teaching and learning based optimization algorithm for distributed and costing job shop scheduling problem. You can see March 2022, latest only. So job shop scheduling problem. And next is, of course, that is related to some parametric optimization. And then modified teaching learning based optimization for selective harmonic elimination in multi-level inverters. Next problem, you see multi-objective elitist feedback teaching learning based optimization algorithm and its application. And in the fourth case, they have applied to discrete sizing design of steel truss bridges. That means structural engineering. Structural engineering they have applied. Then here 3 objective optimization of boiler combustion process. That means for multi-objective optimization, they have applied this TLBO algorithm. And optimal phasor measurement unit placement for power system. This is by electrical engineering people. You people belong to electrical engineering, so you can understand this paper better than me, because I know that researchers are using this TLBO algorithm and to their advantage. I really welcome that. I really appreciate them. Whoever uses this TLBO algorithm to solve the problems. And similarly, here you can observe energy reports, adaptive TLBO with experience learning to identify photovoltaic cell parameters. And many papers improving TLBO algorithm by a distance witness learning strategy. And similarly, here they added teaching learning based algorithm with Gray Wolf optimizer, May 2022. So these are Indians, Navanita Banerjee, Sumitra Mukhopadhyay. And now if you see here, quantum TLB, that means what I can say, different optimization researchers in the field of optimization, they have modified, they have improved this basic TLBO algorithm, and then they made the applications in different fields, not only in electrical engineering or mechanical engineering. They applied in electronics engineering, computer engineering, chemical engineering, and physics, chemistry, that means sciences, and even economics. Economics, they have used, even for training the neural networks. Nowadays, we talk about deep learning, deep neural networks, like that. No? Even neural networks, they are trained by this TLB algorithm. Even neural networks, they are trained by J algorithm. Even recently, I developed RAW algorithms. Those RAW algorithms also gaining popularity, and many researchers are publishing research papers using RAW algorithms. And these TLBO or JA or these RAW algorithms, they can be used for training the neural networks. Training the neural networks, because in the neural networks, you get those weights. So how to get those weights? How to tune those weights? That is done by this TLBO algorithm or JA or RAW algorithms or such algorithms. So different research optimization researchers, they have applied in different fields: mechanical engineering, electrical engineering, civil engineering, including structural engineering, manufacturing engineering, electronics engineering, computer engineering, different sciences fields like physics, chemistry, and even mathematicians, they have used TLBO algorithm. And economists, they have used TLBO algorithm. Many such applications are available. And here, large-scale bound constraint optimization based on hybrid TLBO algorithm, and so many. I need not read one. There are so many. Here you can see this is interesting paper. Modified TLBO by orthogonal learning for optimal design of an electric vehicle charging station. Design of an electric vehicle charging station. For that design, they used this TLBO algorithm. Some modification they have done, and then they applied that. Similarly, you can see just one more screen I show you, because there are many papers available in Science Direct. And overall, okay, let me show you just next screen. After that, I am not going to bother you. And just let me, okay. Let me just see this. Let me see this. This is not working. Okay. Overall, let us understand this. Okay. Application, last paper, if you see, application of TLBO in rotor fault diagnosis for asynchronous motor. And so there are even, if this 49th paper, if you see, energy efficient TLBO approach for common content distribution in mobile ad hoc networks. So many papers are there. I can say so far, using this TLBO algorithm, you believe it or not, thousands of papers, research papers have been published. Thousands of research papers have been published, and one of the estimates is more than 12,000. More than 12,000 research papers have been published using this TLBO algorithm. Using this TLBO algorithm, you can try this because codes are available on the website. Not only TLBO algorithm I developed in 2011. After that, I developed another simpler algorithm, J algorithm, in 2016. and that is simpler than even TLBO algorithm, and equally efficient. Then in 2020, I developed three more algorithms. I named them as RAW algorithms, and RAW 1, RAW 2, RAW 3. Those are also simpler. Particularly RAW 1 algorithm is the simplest. RAW 1 algorithm is the simplest. That is also available. You just type RAW algorithms in the Google search. You will come across that website. Codes are available in Python as well as MATLAB and Python for unconstrained problems as well as constrained problems. And if whatever is your research problem, you take that code available on the website as a reference, and then write your objective function in that, make some suitable modifications to the code and run it. Then that will work. That will work. And with this, actually being director of our NIT Surat, I have actually very busy engagements. Actually, in the morning also, in fact, I was not sure whether I would be able to deliver this lecture or not. Because today we are hosting a number of participating institutions across nation under Unnat Bharat Abhiyan. Unnat Bharat Abhiyan. Under that scheme, today and tomorrow, 2 days of workshop we are organizing. Participants from different institutes, NITs, IITs, and all the participating institutes of Unnat Bharat Abhiyan. About 100 participants they are here now. I am actually sitting in the guest house only now with this laptop because I have to deal with them, being the host, being the host. So at least this much time I could spend with you. And if there are any doubts, you can write to me because my email is available. Simply you search my name, R. Venkatarao, NIT Surat. You will come across my mobile number and email address also. If you have any doubts in TLBO algorithm or J algorithm or RAW algorithms, you can simply write one email to me, and I will be very happy to reply to you. Thank you, Aparna, and all other members of the organizing team. Thank you very much. With this, I am taking your leave.
Thank you, sir. Thank you very much. If I am not wrong, for all of us, this is our first time to get understand how exactly any algorithm can be well explained to the learners like us. Hope all participants agree with me. And since sir has already left the meeting, in spite of his busy schedule, he has spared his valuable time with us. So thanks a lot to Honorable Dr. Rao sir, and thanks for all participants for showing patience and also all their hope attentive in the session. So with this, I conclude today's session. Thank you. Thank you to all. Next session on will be at 3 p.m. I might be doubtful whether because just now sir told us that he will be having deals with